Okay, 1.3 is pretty simple, but I feel like the way that the solutions manual shows it isn't super clear, so I'm going to show it in a couple different ways. But 1.3 says to show that a change of phase doesn't affect the probability. So what that means is, so we know if we have a state like this, we'll just do a simple one, 1 over root 2 up plus 1 over root 2 down. We know that this is normalized because if you square these and add them together, that's going to be 1. And we also can kind of just see by now that the probability of it being down is going to be 1/2 and up is going to be 1/2. We can show that real quick. So let's say probability of it being down, so inner product with a down state is going to be equal to this down bra times the state 1 over root 2, even though now we know this is going to cancel out, but I'll write it anyways, 1 over root 2 down. Okay, so our minus and plus cancel out. We're going to be squaring this because it's probability. And then we have our minus and our minus, so 1 over root 2 squared is going to be equal to 1/2. So there's a 1/2 chance with this initial state, there's a 1/2 chance that we would get a down state. And then 1/2 state would be up. So what this question is asking is, if we were to add a phase to this, prove that the probability doesn't change. So let's go ahead and change this to, let's say 2 equals 1 over root 2 up. And this is suggesting we use a phase of e to the I delta 1 over root 2 down. And it's saying that proves that adding this phase here does not affect the probability. So now if we were to, again, get the probability of being in the down state, so we have our down ket with our new state here, 1 over root 2 up plus e to the I delta down. Minus and plus cancel out, minus and minus we keep. I keep forgetting this 1 over root 2. Okay, again, we're going to be getting the square of this for the probability. So we keep the minus and minus, and that's going to be e to the I delta 1 over root 2, won't forget it that time, and then square it. Okay, so to square this, we need to take the complex conjugate. So first we do e to the I delta 1 over root 2 times the complex conjugate e to the negative I delta 1 over root 2. Hopefully you can see by now, if you couldn't already, if you didn't already know what was coming, you see it now. E to the I delta minus I delta is going to be e to the 0. So we're going to e to the 0, and then 1 over root 2 times 1 over root 2 is 1/2. E to the 0 is just 1, so that equals 1/2, which means we still have a 1/2 chance of it being in the down state, even though we added this phase. So that's showing that in this case, adding that phase doesn't change the probability. Now, is that proof that it's never going to affect the probability? No, it's not a complete proof, but it does show in this case that it works out. Now, what the solution manual shows, which I was saying I didn't find it as straightforward, is to do something like this. So we know that the probability is going to be the, how did it show? Yeah, so any basis vector. So we were using the basis vectors plus and minus before. This is just the two basis states for the spin 1/2 system. But it's saying you could have any of these basis states inner product with our phase, and the probability would be that squared. That's how you get the probability. So it's saying that if you were to add a phase here, then you would now have an inner product with this phase of e to the I delta and then our state. And then it's saying because this is a scalar, you can pull it out, and that would equal e to the I delta a n squared. Okay, and then you can just square this, and again, same thing. So e to the I delta times e to the negative I delta is going to cancel out. That's going to be e to the 0. So that cancels out. So this is equal to a n inner product with our state squared, which is the same thing we had here. And because these two things are the same, let me point it to the right thing, because these two are the same thing, then that is proof overall that adding the phase isn't going to affect the probability.